I'm beginning to talk about friction versus pressure.
When work, sleep,
One of my favorite things.
Thank you. Let's begin by talking about friction versus pressure. Even when a single force is applied to an object, it is usually not the only force affecting the motion. This is because of our old friend friction. Friction is a force that always acts in a direction to opposed motion. We know that already, so I'm reinforcing that. Right? Always opposite motion. What if there is no motion?
Good.
No? Opposite to the direction that it would move if there was no friction, right?
Oh, here we go.
As I was saying,
We have one man.
friction is a force that always acts in a direction of opposed motion. It's due in large part to irregularities of the two surfaces that are in contact. Even very smooth surfaces are bumpy when viewed with a microscope. When an object slides against another, it must either rise over the irregular bumps or else scrape them off. Either way requires force. The force of friction between two surfaces depends on the kinds of materials and how much they are pressed together. Rubber against concrete, for example, produces more friction than steel against steel. That's why concrete road dividers are replacing steel rails. You would see these way back in the 70s. You would see, you really don't see them much anymore. Maybe on old bridges, you would see a post like this, and then there would be like a thing like this, and there's like a steel sort of, you still see them on old bridges, right?
A lot of places in Garden Mountain still have it.
Is that right? Okay, yeah, they are around, kind of. Why are they no good? The concrete road divider, which now looks like this, it's kind of flared, right? No, it's right there on your picture. It's right there. Okay? Why are those concrete ones better? Well, because when the car tire comes up, what does it touch? It touches the concrete with its rubber wheel, as opposed to the steel on steel, which doesn't have a lot of friction at all. So that, the second one, slows you down considerably. Notice that when the concrete divider is wired at the bottom, so the tire of a side-swiping car rather than the steel body making contact with it. Greater friction between the rubber tire and the concrete is more effective in slowing the car than the contact between the steel body of the car with the steel rail on the other side. Friction is not restricted to solids sliding over one another. Friction also occurs in liquids and gases, which are called fluids. Fluid friction occurs when an object moving through a fluid pushes aside some of the fluid. Have you ever tried running a 100-meter dash through waist-deep water, or just exercising in the pool?
Oh, yeah.
The friction of liquids is appreciable even at low speeds. Air resistance, the friction that acts on something moving through air, is a very common case of fluid friction. You don't notice it when walking or jogging, but you'll notice it for higher speeds, as in skiing downhill or skydiving. When there is friction, an object may move at constant velocity while a force is applied to it. In this case, the friction force just balances the applied force. The net force is zero, so there is no acceleration. For example, in figure 4.9, the crate will move at a constant velocity when it is pushed just hard enough to balance the friction. The sack will fall at constant velocity when the air resistance balances its weight. And when the air resistance and the weight are balanced, what is that called? Terminal velocity. It's as fast as you can fall, right? Terminal velocity. Remember the penny one? Like the penny drop off the New York there? I want to say the Eiffel Tower, but that's not right. The Empire State Building, thank you. Mythbusters. Turn your page sideways so you can read the questions in the dark box there. Figure 4.6 shows only two forces acting on the book, its weight and the support force of the table. Doesn't the force of friction act as well? There's the book, just sitting there. Weight force down, normal force up. Shouldn't there be friction on there? Why not?
There's no motion.
There's no motion. Does there have to be motion for there to be friction?
No.
No, but there has to be another force. Like here, these forces are balanced, right? If you come in and you just lightly push with, say, 5 newtons, you will likely see a 5 Newton friction force, right? Friction magically appears if needed.
So friction's always steady. It's not always active.
Well,
I
friction
suppose,
can
yeah.
never be more than the applied force, so if no applied force, no friction.
Exactly. Friction can never be more than the applied force. Okay, so that's sort of a brief review about friction. Friction in a nutshell. Let's talk about pressure now. Flip the page over. You can put a book on a table, and no matter how you place it, on its back, upright, or even balancing on a single corner, the force of the book on the table is the same. This can be checked by doing this on a bathroom scenario, where you'll read the same weight in all cases. Balance the book different ways in the palm of your hand, Although the force will be the same, you'll note the differences in the way the book presses against your palm. This is because the area of contact is different in each case. The force per unit of area is called pressure, or even you could say the weight per unit of area is called pressure, or P equals F over A. I'm not asking you to solve any problems. I just want you to know kind of the difference. Where P is the pressure and A is the area against which the force acts. Force, which is measured in newtons, is different from pressure, which is measured in newtons per square meter, called a Pascal, which is a relatively new unit adopted in 1960. And even on the weather network or on the radio, you might hear them talk about the barometric pressure rising or falling in so many kilopascals. What's a kilopascal? 1,000 pascals, that's all, right? So Pascal is the unit of pressure. Pressure when you're putting air in a tire is usually referred to as PSI, which stands for pounds per square inch. A pound is a unit of force, the inch is a unit of area. Pounds per square inch can be converted to pascals. I don't know the conversion factor, I'm not that nerd. Contrary to popular opinion. Many people mistakenly believe that the wider tires of drag racing vehicles produce more friction. But the larger area reduces only the pressure. The force of friction is independent of the contact area. Wide tires produce less pressure and narrow tires produce more pressure. The wideness of the tires reduces heating and wear. Because they're moving so fast and there's so much heat generated, they're trying to reduce the heat and the wear, otherwise they'd be changing tires like constantly. You exert more pressure against the ground when you are standing on one foot than when standing on both feet. This is because your area of contact is less. Stand on one toe like a ballerina and the pressure is huge. The smaller the area that supports a given force, the greater is the pressure on the surface. You can calculate the pressure you exert on the ground when you're standing. One way is to moisten the bottom of your foot with water and step on a clean sheet of graph paper marked with squares. Count the number of squares contained in your footprint. Divide your weight by this area, and you have the average pressure you exert on the ground while standing still on one foot. How will this pressure compare with the pressure when you stand on 2 feet? Well, on 1 foot, your pressure would be more. You can even imagine, if you stand on 1 foot, you can just feel your foot flattening out, right? More pressure. A dramatic illustration of pressure is shown in figure 412. The author applies appreciable force when he breaks the cement block, it's concrete actually, with the sledgehammer. Yet his friend who was sandwiched between 2 beds of nails is unharmed. This is because much of the force is distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nail points results in a tolerable pressure that does not puncture the skin. Caution, Nate. And if the word Nate is not on your sheet, you should write it in.
Okay.
This demonstration is quite dangerous. Please do not attempt it on your own.
But it still hurt.
Yeah, you'd feel it.
Like how much?
This is a physics teacher.
Like if I did one.
Yeah,
That's like on Jackass when they step in the bed of nails.
yeah.
It's bad. You're my physics teacher. How about you go into the nails and.
I'd be afraid of you swinging a sledgehammer at me.
Let's try.
If only I had some video of it though.
Wait, there's a sledgehammer at him?
On the piece of
Eh?
wood.
Oh yeah? I think I've seen that, yeah. How about we answer these 2 questions, then I'll search for the video. In attempting to do the demonstration, figure 412, would it be wise to begin with a few nails and work your way up to more?
No.
In fact, it would be wiser to do the exact opposite. Many, many, many more nails and work your way up to less. The massiveness of the cement block plays an important role in this demonstration. Which provides more safety, a less massive block or a more massive block?
More massive.
More massive.
More weight.
More massive because it will reduce the acceleration of the board down.
It's all distributed.
Oh, hold on. A 2.5 kilogram crate. So our mass is 2.5 kilograms. It's pushed horizontally with a force of 30 newtons. So the applied force is 30 newtons. If the coefficient of friction is 0.2, calculate the acceleration of the crate. So mu equals 0.2, right? Okay, so let's draw a picture. I saw several pictures out there. That was good. Applied force, friction force. I drew the applied force bigger. Why did I do that?
Because it is bigger.
How do you know? Because it's accelerating, right? So the way to get the acceleration is to find the net force, right? Okay, so we really need to find out what mu is. Start by finding the weight force. Mass times gravity. So 2.5 times 9.8, 24.5?
Yeah.
Honestly, man.
24.5 newtons.
Yeah.
Mu equals FF over Fn. The mu value is 0.2. So I'm going to take my 24.5 and I'm going to multiply by 0.2 and I get 0.1 would be 2.45, so two of those would be, I can't do it, too much. Help me out. How much? 4.9? That seems about right. So the friction force is 4.9 newtons. Now we go to... Okay, Nate, seriously, man, you're going to have to leave. You're going to have to, Nate. People are trying to concentrate. You're disrupting them. 30 plus minus 4.9 is 25.1, right?
Yep.
F net is equal to MA. 25 point, whoops, decimal place.
Can you slow down?
Sure. Okay, so now I'm going to go F net equals MA. 25.1, the mass is 2.5, giving us an acceleration of basically 10, isn't it?
10.04.
10.04 meters per second squared.
Is the power bar?
Okay, so we got 10.04 is the acceleration, but the question actually asks for how far does it move after 4 seconds? Oh, there's quite a bit more to do there, isn't there?
Yeah.
Right?
Just a little bit more.
A equals delta V over delta T. Let's just round that to 4 for easy figuring. 4 seconds. Making my delta V 40, right? Which means the final velocity is 40. So now we're going to solve for V bar. Holy, there's a lot of steps here.
Quite a few.
V bar is 20. And the last step, yep, 80 meters. If you can do a question like that, you are in good shape.
We just did that right here. Actually, she did.
Okay? A lot of steps there.
We did that.
Okay, flip both your question sheet and your big tablecloth over, and you've got until 3:25 to do this one. Now, if you've done these helicopter questions, you'll find no problem here at all. This is a gravitational field question. There is no friction involved here. You have 10 minutes. This particular question, you will see on the test. I guarantee it. Okay? And I suggested that I assigned them a while back, and I thought that I did say you really should do those ones. Here's how it works. Charlie's flying a helicopter and is rising at 4 meters per second when she releases a rock. So the initial velocity of the helicopter is 4 meters per second. Is the initial velocity of the rock also 4 meters per second?
Yes.
Yes, the rock is inside the helicopter. What is the acceleration? Minus 9.8. If you were on the ground, you would see the helicopter rising at 4 meters per second, right? And if you were on the ground, you would see the helicopter do that, and you would also see the rock do that. Why would you see the rock go up and then come back down? Got an initial velocity of 4 meters per second. So yes, the rock actually does travel upwards to begin with. Okay? So what is the rock's velocity after? A equals delta V over delta T. So you got to be careful, because when the initial velocity is not 0, trouble brewing, right? Minus 9.8 is delta V over 3 seconds. Delta V V is 3 times 9.8, which is minus 29.6, am I right? 29 oh yeah. 29.4. Is that the final velocity? No, why not? Because the VI is not equal to 0. So the delta V is minus 29.4. Minus 4, that minus 4 goes to the other side and becomes plus 4. So 4 minus 29.4 minus 25.4. Right? And I'll pause there for a second and let you get caught up. The VF is not the same as the delta V because the VI is not equal to 0. If you miss that step, the rest of it falls apart, right? However, if you show your work, you'll get credit for it. So there would be 2 marks for that. And then in part B, how far has the rock fallen? You are looking for the displacement. And the displacement is based on the average velocity, which you're going to have to calculate. The initial velocity is 4. The final is minus 25.4, giving us 21.4 divided by 2, right? Minus 10.7. Now you go V bar equals D over T. Three seconds? Yeah. Minus 32.1. The rock goes down. It ends up 32.1 meters below where it was thrown out. Is it 32.1 meters below the helicopter curve? Why not? Because the helicopter's continuing to rise, isn't it? How do we figure out how far the helicopter has risen? Yep. The velocity of the helicopter was 4. The time is 3, so the helicopter rises by 12 meters. No, you don't have to. The helicopter rises 12 meters, the rock falls 32.1. So the difference that they are in the end, you really just want to know how far apart they are, 34.1 meters.
44.1.
44.1 meters. Did you guys get that?
We got it all. The British powerhouse.
The dream team. All right. We'll have to do some more reviewing over the next few days. I'm going to come around and pick up your cards. Oh, I did. My six is here. You guys should let yourselves go to New Year's Eve. No,
Oh, wow.
That's true. No, I didn't have no idea what to do.
Low blow. Low blow.
Please help me every time. So, together.